I've known David for the 30 years that I've been involved with the Computational Science Graduate Fellowship. And what I really want to say about David is he really cares. He cares about the next generation. He's a great mathematician, and you can look at his papers and see what he's done in that field. But I want to talk about how he's cared for this program for 31 years, along with his cohorts, Jim Hack and Bob Voigt. They have seen us through some times when we thought we were going to lose the fellowship. And David really, really cares about making sure that this fellowship is the best that it can be, that the fellows that we get are the best that we can get. And I like to say that David, who has been at Los Alamos, then he went to Livermore, and then he went to Berkeley, you could track where David went by that's where the practicum students were going. And I mean, if you can go back and tease the data out from the early years, peak at Los Alamos, peak at at Livermore, but then he kind of, when he went to Berkeley, he handed it off. But he's been working with a former CSGF alum, Marianne Lung, with Sustainable Horizons to bring in a diverse candidate pool to make sure that Berkeley has the broadest diversification of students possible. And like I said, David is a great mathematician, but I think your legacy is really bringing in the next generation. And with that, David is going to tell us about, I talked about 70 years of computational science, and David is now going to talk us about the last 50 years of those 70 years and what it means to be a mathematician.
Thank you. Am I on? Okay, great. Well, thank you, Barb, for that introduction. And it's really an honor to speak here at this meeting. I don't think I've given a plenary since we were in Pleasanton, which was last century. Okay, so as Barb mentioned, I've been at the National Labs for almost 40 years. I just retired from Berkeley Lab 2 weeks ago. I haven't really managed to successfully retire. I had to prepare this talk, for example, and as she said, I've got some other little projects going on with diversity programs and so forth. But I wanted to talk about mathematics. Applied mathematics is one of the important components of computational science, along with computer science, and then, of course, whatever science or engineering you happen to be working in. And I thought that rather than talking about my last 40 years at the labs, I'd give some examples of what I was doing in those days that they weren't called practicums, but in my summer internships, and how that fit into sort of the timeline of the development of applied mathematics as it supports high-performance computing. And so hopefully you'll find this interesting. So, I've got to be the fourth person that has gotten up here and said, okay, we broke the exascale barrier, and everybody should congratulate Oak Ridge and so forth, and the exascale computing program. So, you know about that. Here are some statistics. I mean, 25% of the entire top 500 performance is in that one machine. It actually, this was on one of Barb's slides too. I mean, it reached 6.8 exaflops on the AI benchmark, which is mixed precision arithmetic, mostly 16-bit floating point. I'm not going to spend too much time on that, but I did want to put up this slide, which I got from Jack Dongarra, who many of you know recently won the Alan Turing Award in computer science, which is sort of the Nobel Prize for computer science. And he along with Eric Strohmeyer and Horst Simon, keep track of the top 500 and have done so since 1994. And what this graph shows is where the number one machine has been in terms of performance on the LINPACK benchmark for the top 500, where machine number 500 is, and then what the total sum of performance has been for all the machines in the top 500. So right now it's at 4.4 exaflops for the top 500 machines. The real reason I wanted to show you this slide was because Jack always likes to tell you about his laptop. So Jack's laptop, and that's Jack right there, and this is not really his laptop. I couldn't find out what he actually owns, but but this one had the coolest screensaver on it, so I put it up there. So it clocks at 166 gigaflops per second, which is about 3 times faster than the fastest machine in 1994, which was a Thinking Machines CM5 with 1024 processors, which was the first parallel computing machine, as far as I know, that was used at one of the national labs for serious computations. In fact, I got to run on this machine for a month or so until the weapons program sucked it into some black place and we never saw it again. So by that metric, it must have been pretty good. But this is not the point of my talk at all, actually. I mean, it is partly. I pulled this graph. This graph came out of this report, which is almost 20 years old now. David Keyes, who, by the way, is one of the steering committee members for this fellowship, together with a whole bunch of people. In fact, I found my name in this report. Put together this report on really the science-based case for large-scale simulation. This was actually making the case for computational science more broadly than just a few places that it existed, 20 years ago. And there's a graph in there which shows. So this line here. So what it shows is over a period of 20 years, what the increase in speed, what the increase in performance of codes was. And the bottom line, shows what the hardware advances were. So that's equivalent to the top 500 line that I showed on the last slide. And you can see that over 20 years, there was almost 3 orders of magnitude increase in the performance of the computers. But over the same period of time, just through improved algorithms, there was another 2 orders of magnitude improvement in the performance of the codes. And through improving the models that were used, so the PDE models, for example, another order of magnitude. So the mathematics was responsible for just as much of the performance increase as the computers themselves. And so that is really important because that means that, and this trend has been consistent over the last 50 years, and this is actually what really gives us such fantastic performance on these big machines, are the innovations that are made in mathematics and computer science that help scientists get their work done. And so a lot of what I'm going to talk about in this talk is sort of the background behind how we got there, and this important point, which is to look at the mathematical structure of the problem that you're trying to solve and use that to improve performance of your codes, speed up the calculations. So this, here's a timeline. So this does go back 70 years, Barb, at least. And the original applied math program came into existence right about here, the original program behind Oscar. So the main point I wanted to make of this slide is that the mathematical tools that people used on the computers were not ready-baked and ready to go when the computers showed up. They were all developed during the same period of time, right? And if you go back, I mean, ENIAC was the first real computer that was available. It was developed at Penn, 1946. By the way, the transistor wasn't invented until 1947, so this was a bunch of vacuum tubes. And ILIAC 1 was a machine at Illinois in 1952. ILIAC 2 was in 62, and then we have a CDC 6600, which was the first machine that was really called a supercomputer. and it came out in about 1965. And during this time, a lot of things happened. I mean, for example, the Metropolis algorithm for Monte Carlo was invented in 1947, simplex method, 1947. First numerical weather predictions happened in 1950. First hydro calculations at Los Alamos were in 1948. That's sort of the code word for the first bomb simulations on the computer. And, Fortran was invented in 1957. Bernie Alder and Wainwright invented molecular dynamics in 1957, QR factorization in 1961. The concept of astability showed up in 1963. Discrete Fourier transform, no, that's DFT, that is density functional theory, 1964. The FFT was invented in 1965. So all these things were happening at the same time. And this continues to be the case. The way we're so successful at doing science in the Department of Energy and broadly across the country is that like in every aspect of science, we're innovating not only in the scientific space, but in the mathematical and computer science space at the same time. And that's what makes science so successful. So let's see what's on the next slide. The examples I showed, the bomb calculation I said, and even the numerical weather prediction that was done, I think, for the Navy. It was for military reasons that people were interested in being able to predict the weather because you wanted to know whether your ship was going to sink or something like that. But in the 1950s, scientists began to realize the possibility that computers could bring to the science enterprise. And in 1955 at Berkeley Lab, at that time it was called the RAD Lab, Radiation Laboratory, Louis Alvarez, who later won the Nobel Prize, got the idea that you could use computers to analyze the data coming out of bubble chambers. And so that was probably the beginning of the computing program at Berkeley Lab. Here's a little history of computers. So I mentioned CDC 6600 in 1965, 3 megaflops performance. About the same time, the IBM 360 was at 16.6 megaflops. 6600 was replaced by the 7600 in 1969. And then actually the ILIAC 4, which was one of the series of Illinois computers, was the first massively parallel system. And it was actually conceived in 1972, and it was deployed at NASA Ames at Moffett Field, California. And actually the reason that happened was because a few of us can remember what was going on in 1972. But there was a lot of protests over the Vietnam War at the time, and at the University of Illinois, they were worried about the safety of the machine. And so they therefore decided to put it at one of the government laboratories, and that's how it ended up at Ames Lab. I actually saw this machine when I was at Ames Lab, and I will talk about that a little bit later. Now, I put Jack's laptop back up here. Notice that Jack's laptop is 3,000 times faster than the CDC 6600. So none of the machines that existed in the 60s and 70s performed anywhere near the laptop or your phone for that matter. Vector supercomputing was the next big step in computing. And so the basic idea there was if you pipelined the operations one after the other, a lot of the expense in doing an operation was starting up the operation. So if you only had to start it up and then you could pipeline a whole bunch. I forget how long the vectors were. Anybody remember? Maybe 1024 or something like that. You could get enormous speed ups. And so that's what the Krell series leveraged. And the Krells were never really particularly parallel. I mean, I think the YMP might have had 8 processors on it. Yeah, that's right, what I seem to remember. The Krell XMP was the machine I used when I first went to Los Alamos in 1984. Again, Jack's laptop is pretty much 100 times faster than the Krell 1. So what we called supercomputers back in those days were the big, expensive, took all kinds of fancy cooling, and didn't really run all that fast. But we did lots of amazing calculations with them. I mean, every increase, as it happens now, has made it possible to do things that you couldn't do just a few years before. That's been one of the amazing things about a career in computing, is that it just continues to develop, and it's just amazing. You know, nothing gets old or boring. So I did my first internship in the summer of, that actually is me, in the summer of 1973, on the left. The guy on the right is the only photo I could find of the fellow I did my internship with, and this is quite recently. Recently, I couldn't find an old photo, but I did it at CERN, so the European Council for Nuclear Research. Everybody knows where the LHC is. Large Hadron Collider is at CERN, and I was working on magnetic optics design of the super proton synchrotron beamline, which was a big, huge deal at the time. This is a map from probably the 80s, and it shows there's a little tiny circle there, which is the original CERN machine, and the super proton synchrotron beamline was this big circle here, a big tunnel, and they were digging it at the time that I was there, and they were, you know, madly trying to design the beamline at the same time. That's why I was helping Niels, and actually, one of his colleagues was my father, which is how I got the job, but that's another thing. And helping them design the beamline. And this big circle here, this is LEP, that was the Large Electron-Positron Collider, and which was the next machine they built. And then they took that out of that big tunnel, and they put the Large Hadron Collider in it. So that's where the Large Hadron Collider is there. And this is the border between Switzerland and France. So one of the cool things about working at the place where we're running these jobs was that you got to go through this tunnel into France without going through customs every day. Now I guess you can just drive over the border, right? So that was my first real science internship, and boy, was it cool. I mean, that is really what got me going in computing, was this experience I had after my sophomore year in college. So another story I wanted to bring up was sort of some of the story of weather forecasting and then climate science. And so this guy here, Carl Gustav Rossby, was a Swedish scientist he lived in the United States in the early part of the 20th century, and I think he started up the meteorological department at MIT in Michigan, if I'm not mistaken. But in the early 1950s, Stockholm University attracted him back to Sweden, and he started up the Swedish Meteorological and Hydrological Institute, which is what SMHI is. And in 1954, there was a huge storm that caused a lot of flooding in northern in Holland and northern Germany and so forth. And so Rossby collaborated with I think his name was Hansen, a professor at Hamburg University, who sent a young student, 24 years old, named Heinz Otto Kreis, up to work with him in Stockholm. And this is, one of the reasons I'm talking about Heinz is he later became my thesis advisor, but he did a lot of other great things. And this is his wife, Barbara, as well. And so he came up and worked there. Barbara was also a mathematician. She worked as a programmer at Swedish Met, and they met and ultimately got married and so forth. But it was his experiences as a young scientist there that I think led to a lot of the advances that were made in applied mathematics for doing numerical calculations. And I remember him talking about the fact that they had these methods for simulating weather, but they didn't really know when they were stable, why they went unstable, they didn't really understand accuracy all that well. There's a lot of questions that were unknown. And he, as a mathematician, got really intrigued in that, and so he switched from whatever it was he was doing before and basically invented the field of numerical analysis for partial differential equations. And I put up some of his papers here, and I'll just mention what some of them are. This very early one, which I think was actually related to his thesis, was about well-posedness of differential equations. And that's basically the concept of if you specify a problem in terms of mathematics of differential equations and boundary conditions and so forth, can you get an answer from that or not, right? Is it going to be stable as a problem? And then that later led to working on stability theory of difference approximations, so approximations on grids. And he also got into working on problems with different timescales, which these days go by it goes by the term multiscale science, because the problems in meteorology have multiple scales. And actually, one of the interesting things that he was trying to understand was that the equations that, for example, the primitive equations, which can be used to model. Jim Hack can correct me if I'm saying incorrect things about meteorology, but can admit solutions that are, in some sense, unphysical. So you can get a lot of waves floating around that don't actually really show up in the weather, but numerically can be excited if you don't do things properly. And if you specify the boundary conditions or the initial conditions incorrectly, you can excite these waves. So there's a lot of mathematics that went into understanding how to properly set the boundary conditions and the initial conditions so that wouldn't happen. And the theory for so initial boundary value problems, which means time-dependent problems with boundary conditions, was really important. And one of the interesting things that was discovered is that some equations, that describe physical processes that people understand, there are no well-posed boundary conditions for those equations. In other words, the only domain you can solve those in is either on the surface of a globe or something that's infinite, right? There's no way to specify boundaries. Every possible boundary condition is unstable, and so those were some really interesting results at the time that were not understood until really the early 70s. This paper I worked on, so stiff boundary value problems is also a multi-scale problem. That's partly what I worked on my PhD thesis, and I did put the paper that has some of my PhD work up there too. Let's see, anything else? And also I should mention, and Barbara herself actually published a number of papers as well, but worked for many years as Heinz's main programmer. In fact, he would give problems to his students to solve, and then he would sort of secretly give them to Barbara, and then he would compare the results because he trusted Barbara, but he didn't necessarily trust us. So that was a good quality assurance thing. I shared an office with Barbara for a number of years at Caltech, and she was a really wonderful person too. I'm sorry they're both gone now. So by the early 1970s, people were beginning to understand the advantage of high-order methods, and the fact that if you used high-order approximations to different differential equations, you could actually get a lot more bang for the buck, right? It required fewer mesh points for a given amount of accuracy, and you could take much larger time steps, which meant you could do a lot more computing if you could take advantage of them. The flip side was that actually, when you go to higher order difference methods, the boundary conditions become more difficult, and so that actually it took really until the last couple of decades before people seriously started using higher order methods on real problems because the boundary conditions were so hard. But one of the concepts in this paper, and let's see, Joe Oliger here was a professor at Stanford. Actually, he was the first professor that I took numerical analysis courses from when I was an undergraduate, was a co-author on a couple of these papers. And these are the papers that introduced the concept of phase error and points per wavelength. So before that, people looked at asymptotic convergence, like, is the method second order or fourth order or sixth order or whatever, which really didn't give you that much useful information, whereas the concept of how many points per wavelength do I need to properly resolve, this weather pattern is a lot more useful concept. And so they introduced sort of the Fourier analysis technique for looking at that and how to understand that. I mentioned this because my next, how am I doing on time, by the way? Okay, and I have an hour and a half? Apparently not. Okay, so I'm going to take a little sidetrack here because this is related to my next set of internships. So in reflection seismology, which is a field of geophysics where basically you're looking for oil, so what do? They go out and somehow or other they excite the surface of the Earth. It sends pressure waves down into the Earth. They reflect off of the interfaces down there, and from the reflections you can figure out where the changes in material density are, and hopefully find things like where oil might be trapped. I mean, that's a kind of a simple story of how it works. And the data sets kind of look like the physics. So this is the top is. Really wish I had a better laser point. The top is some data. So this is time series data that's collected, and the bottom is process data that's supposed to show. Like here, you can see a dipping layer, and then there's these little humps there are really interesting because they tend to be places that trap oil or gas or whatever. And so this picture over here comes from this book here, which, by the way, is one of the worst textbooks I have ever read. It was John. This is John Claerbout who wrote it, and he was the professor I worked with. But it was so bad that it was just really intriguing. And this is. And so I really wanted to find out how this stuff worked because it was clear, you get all these interesting answers and nobody could figure it out. I mean, we would get together with all the students after class and sort of try to figure out how to do the problem sets. And in the end, I ended up working with him. And it turned out to be very interesting. Anyway, so here's an example of a synthetic here. So often, they're doing this, they're looking for oil under the ocean, right? So this is meant to be a seabed. This is the reflectors underneath there. And so the second picture here is what the data looks like that comes back from that. And you kind of see, things that kind of look like those two beds. And then this other stuff here is multiples, meaning it's waves that went down, came back up, and reflected one time, and they end up taking the shape of the layer at the top, which is the seabed. And then there's this process called migration, which then turns around and gives you back something which, in this case, since there's no noise in the data, can be pretty much exact, get back what the actual answer is. So something called wave equation migration was very popular back in the 1970s. It was invented by John Claerbout in the early 70s, and it was in this book. So that's kind of the background for the next slide. So I ended up working with his Stanford Exploration Project for 3 summers, and did a lot of mathematical analysis related to. One thing was one-way wave equation. So basically, the reason it was called wave equation migration was because you used a one-way version of the wave equation to do the imaging. And then a lot of the work I did was on accuracy of wave propagation for forward modeling. So forward modeling just means making synthetic data sets that they could then use to test out algorithms and so forth. This paper down here on splitting and separation was helping to explain mathematically what processes in some of this very, very complicated data processing could be done separately and didn't have to be done together. And so, for example, there was something called pre-stack partial migration, which this basically justified why that worked. So that was really interesting. I learned a lot in those summer internship activities back in those days, and that really impacted a lot of my thinking too, and taught me a lot of things about numerical analysis that I used later in my career. Let me switch to another place that was really hopping in the 1960s and 1970s was NASA, because some of us recall the space program started basically in 1960 or something, or 59, and NASA was busy trying to design things like the space shuttle. And so CFD, really a lot of the research that happened in CFD happened at the NASA labs. These examples are from NASA Ames, but there's also NASA Langley on the East Coast. And this, so here's an example. I mean, this is looking at that's actually the space shuttle there, and then those are the booster rockets dropping off, and they needed to make sure that the booster rockets didn't spin around and run into the shuttle when they were dropping off and stuff like that, and you could figure out whether that happened using CFD calculations. So this paper here, the effective viscosity and hypervelocity impact cratering, which sounds very scientific. When you read it, there's about a paragraph on that subject, and the rest of it is the introduction of McCormick's method and an analysis of the stability of the method at the time. So this is one of the first methods that was used for CFD calculations. It was an explicit calculation. So for those of you who know what that means, since he was doing Navier-Stokes, which has viscosity in it, the time steps would have been limited by the viscous terms, which meant you had to take lots and lots and lots and lots of time steps to get answers, which they did. In 1977, Beam and Warming, another couple of people at NASA Ames, invented the first implicit method for solving the Navier-Stokes equations, which meant they could do the calculations like 100 times faster than they could before, right? So just that concept of going from explicit to implicit methods made a huge difference in what people could compute on those machines. This paper over here is on fast conservative schemes for full potential equations. One of the authors was Terry Holst, who was my mentor at another internship I did at NASA Ames in 1980, and in which I worked on, and you'll notice I'm slowly losing hair, you'll see as the pictures evolve, and it moves lower down on my face and things like that. So, but one of the things I was working on with Heinz Kreis at Caltech at the time was adaptive mesh refinement. And so I, with Terry, looked at how to do adaptive mesh refinement for two-dimensional airfoil, calculations of flow around airfoils. And this paper, I got one of my first papers out of that. Oh, that's not my pointer, that's okay. One of my first papers out of that, and one of the things it said was, just by moving the points around a little bit on the surface of the airfoil, which was done adaptively by looking at solutions that were computed iteratively, you almost doubled the accuracy of the calculation with the same number of grid points. So that was sort of unknown at the time. I mean, that was a kind of a really big deal in 1980. And that particular kind of mesh refinement is not what ultimately took off, but people were doing all kinds of different things at that time, and it was really interesting. What actually did take off was block structured mesh refinement, at least for finite difference and finite volume methods. And if you look back in the literature, you can see the original ideas actually showed up. One place was in Aki Brandt's early papers on multigrid, which I was surprised to see went dated all the way back to 1972. I didn't realize it was that long ago. And you can even see a figure out of that paper where at the time he was thinking about adaptive local refinement in multigrid rather than what's typically done these days, which is just to refine everywhere, right? But also Joe Oliger, who I mentioned before, wrote a paper with Heinz Kreis, and this guy Jerry Browning was at NCAR, at the time on mesh refinement and explained, what the advantages of that would be. And the basic advantage is if you can focus calculation only where stuff is really happening, so put fine meshes where stuff is really happening, and then use coarse meshes everywhere else, you can get enormous improvements in performance again, because you're using much fewer degrees of freedom, number one, and number two, in all the areas that you don't have to put fine grids, you can take much longer time steps. In fact, essentially those parts of the calculation are practically free. So, one of Oliger's most famous students is Marcia Berger, who her PhD thesis was on adaptive mesh refinement for hyperbolic partial differential equations, and she later worked with Phil Colella he was probably at Lawrence Livermore at the time, on doing this for shock hydrodynamics. And in the next slide, I'll show a little bit about how that's evolved. Interesting thing is that in her original thesis, the refinement meshes were not aligned, which meant that you had to do a coordinate transformation for every single one of them, which made it a whole lot more expensive. And they quickly figured out that it made much more sense to simply refine the grid in a rectilinear fashion, and that's what's currently done today. So this is a sort of a timeline of what happened in adaptive mesh refinement since that time. I mean, we'll go back to 1984 in the original papers, but if you look at, for example, the SIDAC program now and the exascale computing project that Barb mentioned, 6 of the major application codes in the ECP project use this technique that Marcia developed back in 1980, the block structured adaptive mesh refinement. And in fact, there's an entire code-assigned center just on block structured adaptive mesh refinement within the ECP. So I think I already mentioned I was a PhD student at Caltech from 78 to 82, and then I did a postdoc for a couple of years there. While I was at Caltech, there was this crazy guy, Jeffrey Fox, who was pushing the idea of what he called the Caltech cosmic cube. And the basic idea was to build a parallel computer out of the chips that were used to manufacture IBM PCs, which is what you see right here. Those were the original personal computers. And so here's the machine, and he, together with Chuck Seitz, who was a computer science professor there, they built this machine with 64 processors. It could do 3 megaflops. It consumed 700 watts of power, so like 7 light bulbs worth of power, but it could do some pretty amazing computations, and it was really cheap to build. And one of the things was, if you so I think it may have been Barb that was mentioning exawatt, or was mentioning megawatts per exaflop or something like that. So this is the inverse number. But if you look at how many kiloflops you could do per watt on the Cray 1 or the Cray XMP, it was like 1.4 kiloflops per watt for the Cray 1, but the Cosmic Cube could do 4.3 kiloflops per watt, which meant it was actually quite a bit more efficient than in terms of per flop than these expensive machines. And that sort of is sort of a leading indicator, if you like, of what was going to happen later on, because this was clearly a much better way to go. So by 1987, so this is just 5 years later, there were 3 commercially available hypercubes. One of them was built by the Amatec Corporation, which I'm sure none of you have ever heard of. They make manhole covers and just all kinds of stuff. But somebody, I think there might have been somebody on the board at Caltech who had heard about this Cosmic Cube thing and said, oh, we got to get into these parallel computers. So I actually worked for the Amatec Corporation for about a year as a postdoc at Caltech, and that's where I wrote my first parallel computing codes, was on that machine. Anyway, it had 64 processors. In 1986, there was a meeting about hypercube multiprocessors, and if you look at the report, there are over 200, there are almost 200 papers in that report. So in the span of about 5 years, this field exploded. And you know, these early commercial, I don't know who bought these early commercial machines. Let's see, of the three, only one of them is still in the business of doing that. But by 1993, and so if you recall, the very first chart I showed, you know, Jack's laptop was 3 times faster than this machine here, which was a 1024 processor connection machine, and that, in fact, is me standing next to Mike Minion in front of the machine at the Advanced Computing Lab at Los Alamos in 1993. This was one of the first machines that had lights on it. And the purpose of the lights was so you could tell whether the processors were running or not. So a good situation was when all the lights were on. Of course, that wasn't very interesting, and so there were people that actually wrote codes just to turn the lights on and do blinky stuff. Maybe that's why they sucked it into the into the dark side of the lab. Either to write those codes or to get it away from those of us who were doing so. Mike and I were, you know, given the machine gets run through. He was a graduate school. I have 1 minute left. Okay, I'm not going to be done in 1 minute. But I'll try to finish up. He was he was in graduate school at Berkeley at the time, and I said, you know, Mike, let's run some codes on this and just see how it performs. Why don't you do a convergence study on some upward-centered difference schemes and see what happens? And he went in and ran these codes and came back and showed me these pictures, and they were like wrong. I mean, it was like, there's something wrong here. You need to find the bug in this code, Mike. And he went back and checked and came back after a while and says, no, there's nothing wrong with the code. This is actually what is happening. And this actually resulted in 2 papers that we wrote, which basically were all about what can go wrong if you're not careful using, you know, powerful methods on machines. And I think they're still interesting reads. But you know, basically what happens is if you're not well enough resolved and you're trying to solve these nonlinear problems, you can nucleate like vortices in the flow that don't really exist, and then you get lots of really cool looking physics, which isn't physics at all. Pete Eldroth, who was later you know, one of Jeff Hittinger's predecessors running the Center for Applied Scientific Computing at Livermore, later told me, he said, the weapons designers at Livermore were like scared for like a year after these papers came out, because until they figured out how to exactly understand them, because these were like the codes they were using. Okay. There's this great quote I just had to put up there, which came from Seymour Cray. So if you were plowing a field, which one would you rather use, 2 strong oxen or 1,024 chickens? Well, the chickens won, so that was... Okay, I'm going to just skip through some other things. I did want to mention, you know, one thing in multiscale. So the concept of low Mach asymptotic. So basically, this problem of many physical problems exhibit solutions which you're not interested in, but actually make your calculations really slow. So, for example, in nearly incompressible flow, you have all these sound waves floating around that are moving at very high velocities, and therefore you have to take very small time steps if you compute compressibly. And so, using asymptotic analysis, which is, you know, a mathematics technique, you can derive equations which take the sound waves out, and you get these equations for low Mach number flow. And on the one hand, you take out those waves, but on the other hand, you end up having to solve an elliptic equation at the same time, an implicit equation, so it's not a total win-win. but it still is a whole lot faster than solving the original equations. And these methods have also been very successful, and originally they were developed for combustion calculations, but they're used all over the place. In fact, the last this thing down here is a wind farm simulation, which is one of the projects in the exascale computing program. I also wanted to mention this point here. This is a slide that Jim Hack gave me. Actually, gave me a couple of, and I changed the titles because I wanted to make a different point than Jim had made. But basically, I just wanted to point out that, often people talk about, if I just get a bigger machine, I can get more resolution, and so I can do bigger problems, and I'll be able to see more details. And the point of this plot here is that often resolution is not the only thing that you're interested in doing more of. I mean, often there's increased complexity that you want to add to the problems you're solving. You might want to run for very long times, or for example, in climate, you need to do many ensemble. You need to do ensemble calculations. You have to do lots and lots of calculations. And then one of the other thing is that in both weather and climate, you want to take advantage of satellite data that's collected, and that's always changing as well. And so you want to be able to do data assimilation to incorporate the data that you get into the calculations that you're doing. And every one of these axes is something where actually mathematics is really important to help you do it effectively. And this slide here shows, basically what people would like to do in terms of resolution and capability at different levels for climate simulations. And then if you did nothing at all except to get a faster machine, how big would the machine have to be? And of course, the Christmas wish list is over here on the right, and it would take, according to this, a Yotta-scale computer, which I seriously don't think we're ever going to have. And so there's a lot of opportunities, and really the way to get out of this is you got to be clever, right? And that's maybe the main point of my talk here is you got to be clever to make effective use of these machines. Mathematics is a really important part of this, and I'm just going to get to my summary slide. Oh, I did want to mention, and by the way, there's plenty of other things to do that I haven't even mentioned. I mean, quantum computing, quantum information science, there's lots of opportunities for applied mathematics there. Things like quantum ground state preparation, noise mitigation in quantum systems, quantum circuit synthesis, optimal control for realizing logical gates. Those are all math problems. Machine learning for science, how to represent the data for scientific applications is really important. That's a hard math problem. Optimal selection of hyperparameters, that's another example. There's many other examples as well. So this is my summary slide, and really I've already said it. I mean, there's enormous performance gains that can be enabled by clever mathematics, and I hope that you'll all continue to think of this during your time as fellows. This is one of the reasons we built the fellowship, was to make sure that people had a chance to be trained not just in their scientific area, but also in applied mathematics and computer science to the extent that you could be a practicing scientist in all three axes and do really effective calculations and be really successful as scientists. So thank you very much.